All right, so we're back in Building 42, and today we're with Patrick Dussud, the creator of the Garbage Collector, right?
Right.
CLR.
Yes.
How are you doing?
Good.
Excellent. So it's an honor to have you on Channel 9. It's been a while. We've been trying to get you.
Right.
So I think, the obvious thing to begin with would be, what is a garbage collector? Let's start at the very basics. What does it do?
Right. So the role of the garbage collector is to automate the management of user memory. In the old days in C++, you have to allocate memory, you use malloc or new, but then you have to find the right time to dispose of it. And you have to be sure that there is no sharing between, so if you pass it around, you are not necessarily sure when to do it. So that introduced problems in terms of application crashing because you dispose the memory and then somebody is still using it and you don't know that.
Sure.
So memory management is intrinsically, when it's explicit with new and delete, is not composable. You cannot, either you have to be certain that you are in complete control of your own memory. Therefore, you would have, if you want to respect that isolation very strongly, you'll have to copy everything when you pass it to someone you don't know, to another module, and then the other module then will be responsible for managing its own copy of the memory. Or you have to get to a place which has uniform vision over the entire memory pool, and that's the automatic memory management.
Sure.
And that's what the garbage collector does. So a garbage collector essentially is responsible for knowing all of the places where objects get referenced, and then notice objects that aren't referenced anymore and reclaim the memory, and do that in an efficient manner, possibly more efficient than the classical new and delete paradigm.
Interesting.
And essentially, we try to go beyond that because it opens new opportunities. So you kind of turn constraint into opportunities. One example is you need to know where every object is referenced in order to find out if it is indeed referenced or not.
Okay.
But if you do that, then you can slide the object, compact it, move its memory around, and since you know everybody which references it, then you can fix those sites, things that are not available to you in C++. So essentially, if we just did a memory management like new and delete, except we would just automate the delete, then we would be slower than new and delete because we just add overhead. It turns out that by doing intelligent compaction, we can beat the speed of new delete because we stay very compact, so we can take advantage of cache locality, of page locality, and therefore actually we come up positively, especially on very hard to manage servers. For example, most of our server workloads, we actually do better than all of the previous attempts at low fragmentation heaps or anything of the sort. We don't degrade over time, and we give consistent memory management speed.
Interesting. So, a lot of the times what we hear, though, with when someone's trying to think about, do I want to use managed code? Do I not want to use managed code? Do I want to let my objects be handled by something that I'm not in control of?
Right.
And I know that a C++ developer typically doesn't like that.
That's right. It's getting not being micromanaging your object, essentially.
Exactly.
And sometimes it takes either practice or even faith. One of the areas where people are the most uncomfortable with it is when there is an action connected with getting rid of the memory. And that's finalizers or destructors. So destructors, they run exactly when you say delete, you know your constructor is being run in C++. For us, since it's up to the garbage collection to notice that the object is going away, the corresponding destructor code, which is the finalizer, will run at odd times that are predetermined by the garbage collector. So that surprised a lot of people. In particular, we have to be careful of what the set of objects that you do reference from that that destructor code. Because if you are destructing a whole network of objects, the ordering of the destructor code isn't prescribed. So you may end up with destructing leaves first and then the higher level object. But if the higher level object is trying to actually do some side effects on the object it's referring to, then it may fail because these objects have already been destructed. Their code, the memory is still there. We are very coherent about the memory. So all of the objects that are reachable by the object which is trying to execute the destruct code, it's all available, but the state of the object can have been reset by the destruct code of their own. So that's, you have to be careful. An example, for example, is you want the file system is a structure class. At the lowest level, we have a notion of a file handle, which is the OS file handle. And itself has a destructing code. When the file handle class isn't referenced anymore, you want to close the OS handle so you don't leak it. But then we layer on top, and if you do some kind of a text writer, then you have several layers of objects. And they all have a finalization step because we would like to flush the buffers that they contain. So when we finally close the file, then all of the contents that was buffered is automatically done. By the way, it's not the preferred way to operate with text writer. The way to do it is actually close explicitly. Okay. So the first step is for apps to separate the notion of side effect with the notion of lifetime of an object. So if they have something that they need to finish, then they need to provide an explicit method. And so you do close and then you're golden. It's only if you forgot to close and your object now becomes unreferenced, then what's the right thing to do? And essentially, if you don't have a guarantee of the higher level will be able to flush to the down level, then that's going to flush to the down level, etc., all the way to the file handle. If the file handle gets closed first, then obviously it's a problem.
Absolutely.
And we face this problem. We solve it only in one simple way, which is we have what we call critical finalizers, which are encapsulated by our OS handle classes that we have in WIDB, and these are finalized last. So when we have a choice, we have a collection of objects to finalize, we will finalize the critical finalizers last. So essentially the higher level will still see the file handle open until they've done their job. But in general, we don't have, because we don't want to have a complicated graph language to speak about the ordering of finalization code. In general, finalization code should largely disappear and just be there for backstop in case the programmer didn't properly perform the last side effect that he was supposed to do before letting the object go. Okay. Actually, a lot of our finalization code, when we run in debug mode, have a call that says if I ever run this finalization as part of garbage collection, then that's an error. And we raise an error, and then it's up to the developer to fix it.
Interesting. So what are the semantics? I mean, how do you know how do you define a critical finalizer?
You derive from critical handles. It's actually built in the CLR. Okay. So critical handle are you can actually, people can derive from it, but it's really for system code. Okay.
So let's talk a little bit about the history of the CLR,
okay,
garbage collection. What were some of the first challenges that you had to
So the history of the garbage collector is I wrote most of the garbage collectors at Microsoft. The first one that we wrote that was in a product and still there is JScript and VBScript. We got together with 4 people and we decided to write JScript over a few weekends. because we thought, it was a cool way to script web pages, and we had a debate very early on about two approaches. One was very explicit, and the interpreter would generate new and deletes on demand, and I advocated, no, we need to introduce a garbage collector because that micromanagement will cost us too much. So a friend of mine said, okay, I'm going to do the explicit one, and you write a garbage collector, and then we'll see which one wins. And I didn't finish on time compared to him because doing an explicit delete is a lot quicker. But then we started to run his code, and when he discovered that it was so slow, he said, okay, I give up. I don't think that yours can be as slow as mine. And then I finished the garbage collector, and then we did it. So this one was a very simple one called conservative, where we don't have to know all the places that refer the code. If we have an integer that happens to look like an address of an object, then we consider the object live. So we are conservatives. We don't destroy all of the objects that we could. Also, we cannot move many objects because if an integer refers to it and we don't know it's a pointer, it looks like an integer, then we cannot change the contents of this integer because it could be the price of something or whatever. So we can't change that. So it was much more limited and unsophisticated. Then when we started, the same group of friends started the JVM, the Microsoft Java VM, then I wrote another garbage collector for it, which was derived from the JScript one, was also conservative. At the time, all of the JVM were conservative. And then with another friend of mine, who was working externally, but I decided to consult with him, and we decided to say, what if we wanted to write the best garbage collector for Windows, how we would do it? So we worked together, we derived some specs, and then I started implemented it. And the funny thing is I implemented it in Lisp, because at the time Lisp had the best debugging tools, and they had strong protections, all the arrays were bounce checked. And we had a terrific debugger, so I wrote it in Lisp. I wrote a simulator of a JVM in Lisp, debugged it, and then I wrote a code translator that translated automatically my Lisp code to C++ code.
Nice.
And then that was the base of the new JVM garbage collector.
Now, was that a challenge for you to write a filter from Lisp to C++?
No, because I used to work in Lisp companies. I used to work at Texas Instruments on a TI Explorer, and I wrote a translator that was translated from the Zeta Lisp dialect of Lisp into Common Lisp. And we translated the entire system code. We had 3 million lines, and they all got translated automatically. And then we forgot about the old dialect. So I knew how to do that. That's pretty trivial. And when I wrote my Lisp code, I was very careful to use only the functionality that are easily translatable into C++. So it was pretty straightforward. And I had experience in Lisp translators.
So, of course, the CLR's GC is written in C++.
Right. And so when we moved off from the JVM onto the CLR, then I used parts of it as a base, and then we improved greatly. Essentially, in my opinion, the way to write a good garbage collector is to write a solid base which support good mechanisms. So you have something that once it works, you don't want to change too much. And those mechanisms needs to be fairly orthogonal and on time. If you did your architecture right, then you can add some. And then on top of it, you put what I call a policy, and the policy will determine which of the mechanisms to use in which situations. And a lot of the speed and the efficiency of the garbage collection comes from the tuning of those policies. And you detect automatically that the app has a workload that isn't conducive to the normal way of the normal mechanisms, and somehow we detect it, and then we come up with another tuning that will essentially move the app from a very inefficient collection mode into a more efficient collection mode. And essentially, throughout the years, we've been looking at workload, and if a workload looked bad, then you say, okay, what's bad about it? How can we improve the workload? When we know how to derive, this mechanism needs to be done happening at this rate, then the workload is a lot better. Then the policy would actually detect this kind of situation using the relevant factors, and would apply. So the relevant factors are we observe the rate of collections for all of the generations. We observe the internal fragmentations. We observe the memory load. We observe some internal bookkeeping that needs to happen in GC that normally shouldn't cost much, but could end up costing a lot in some situations. So all of those costs and frequencies are observed, and then from there we derive, this mechanism actually is not productive. We thought we were trying to reduce the memory, so we did a full collection because we have a high memory load, but the full collection didn't reveal anything interesting. So next time the OS tells us that we are still in low memory mode, we are not going to put the app into a full collection again, because if nothing happens in between, we are not going to get anything out of it. So those are the examples of dynamic tuning that happened, and essentially the garbage collector embodies a lot of this experience that we have on observing very deeply a lot of workloads from customers, from internal, from partners, and trying to find the relevant factors that either make the application behave great, and we try to repro that, or behave badly and try to shift it into a more efficient mode.
Interesting. So I guess, one of the Niners have asked a bunch of questions, and we'll address them a little later in this interview, because I told them we would, and some of them are good questions.
Right.
And I shouldn't be asking all these questions. Niners are smarter than I am. So, one of the things I'd like to ask, and this was asked too, what defines an object is no longer alive?
Right.
Let's talk about object lifetime.
Sure.
And in a non-explicit context like a GC, the developer doesn't have to say this object is dead.
Right.
Which is why it's composable. As you mentioned,
that's
we should talk about that too. But go ahead and tell me about it.
Okay, so let's start with the beginning. How do you express that you hold an object? So the most, we have local variables. When you say object I equals new object, then I refers to an object. So that's one source. And then another source are static variables. And the third, less interesting source, because it's more complicated, but it's the same, is handles. So you can create handles yourself. But essentially, those are the primary ways for the EE to hold on to objects. And then obviously object will hold on to other objects. So that's the beginning of the graph. So essentially we could consider the population of objects as a graph, or a series of graphs that are rooted. The head of the graphs are all of your local variables on all threads, and all of the static variables that your program has. So that's the initial root set. We call it root set. And actually during the collection there is a protocol between the EE and the garbage collection module, which are clearly separated.
The EE is execution engine?
Right, the CLR. And so when the garbage collector module decides that it's time to do a collection, it calls into the EE and say, please stop all my threads so we can look at the stacks. The EE does that, and then in response, then it says now all the stack are frozen. And in response, the GC says, now you need to explore all of the stack and the static and come back to me with the initial route set. So there is a iterator module, if you like, and the CLR will call into the GC module with one route at a time. And now that route is used as the beginning, and we explore, because we have a static data generated by the compiler, will tell us at which offset into the instance we have reference sites. So we go through all of the reference sites one by one, and we explore them recursively. When we come out of that recursive process, all of that tree starting, or that graph coming from that one route, has been explored. So anything accessible from that route is marked. So we mark in different ways, it's not that interesting, but at the result, we can tell if we go to this object, we can tell has it been marked or not. And either we put something inside of the object that nobody can normally see, or we have an external table. We use both techniques depending on what's more efficient in what situation. But essentially, the idea is you leave a trace, and when you have an object, you can tell has it been marked or not. By the way, it's not the code doesn't reflect the recursivity, because you could have a very, very, very long chain and you would run out of stack space. So instead we use a data stack that just we record the object reference that will need to be explored, and we pop the top, we look at what's inside, and we push all of the reference that we find from this object. And then we keep going until the stack is empty. When the stack is empty, then we've marked all of the... sorry about moving.
No, that's great. Please.
Then we have marked all of the objects that come from that single route. And we repeat that for all of the locals, the registers that contains references, and the static variables. Once we are done, we have exhaustively marked every single object that is accessible from the program. So from now on, we can explore the memory object to object and say, are you marked? Yes, we'll keep you. You're not marked? Oh, now we have a hole. You're not marked? No, we have a hole. And then at some point we will decide either to compact the holes or not. That's up to a policy, but we have a mechanisms that either can compact those holes or not. But that's the idea. Excellent. And that's essentially what we call a full collection, because we traverse every accessible object from the roots. We have way to collect only the parts that have been newly allocated, and that's what we called a Gen 0 collection. Essentially, only the objects that have been newly allocated since that's GC will be looked at. And so for that, we need to find a way to make sure that if an older object refers to this one, we capture that. And we have ways to capture those reference sites spatially, so we can go fast and find them without going through the entire set of all of our objects.
Excellent. So I mean that's a great point to clarify that what generation means for a garbage collector is the last time the garbage collector ran.
Right, that's the newest generation. That's right.
Generation. We
call it Gen 0, and it is widely true that you will find a lot of garbage there. So it's also very local. It's what the cache referenced the most recently, because you just created them, so you had to create them. They had to be in your cache at some point. So if you're lucky, a large population of them is still in there, so they are cheap to work out. It's also a very precious space to compact, because it's a hot space that is in the cache. So somehow, if you could manage to get rid of all of these objects that were newly created, because when you collect you don't need them, and it's all in the cache, then you win big, because you are just cache local. So in reality, it doesn't work out as beautiful as this, but that's what drives you to try to get the new objects first. And the policy engine tries to make sure that it is efficient. if we find out, for example, that we don't really find any garbage object in there, then we back off and say, maybe we shouldn't try to collect there very often because we don't find anything. It's just a waste of time. On the opposite, if it's very productive, we find a lot. We say, okay, that's good. Let's try it again soon. Okay. And that's one way that the policy engine will try to get an efficient workload.
Excellent. Now, I mean, I remember, a few years back there was a big debate, and I used to be a developer and on these technical lists with deterministic finalization,
right.
C++ people. Actually, you worked with the C++ team, so there sort of is deterministic finalization in managed C++ now, right? Or is that, but they're destructors?
Well, they have destructors, but essentially they have a hybrid world. So when the objects are explicitly created and explicitly deleted, the non-GC object, then they have deterministic finalization. That's their own world.
Sure.
And when they have that GC prefix for the manage object, then they don't get it.
Okay.
And we worked. That part is such a heartache. I must have spent maybe six months on these issues on and off, trying to marry both of them, and we never found a good solution. Chris Sells, actually, we gave him some money to try to marry the worlds, and he did it in a pretty clever way, and then he measured it, and the performance loss was at least 2x for moderately high rate of allocation. So when GC was particularly useful, you will pay 2x cost, and that's not something that we feel we can impose on developers.
Certainly.
So our recommendation is only don't micromanage, and essentially at the end we will call all finalizers one way or another, and essentially it works out. What the garbage collector does is it watches over the whole memory and try to make the whole process fairly efficient instead of concentrating on one part of it.
Understood. I mean, it's a generic management platform in a sense.
Right.
And so, it is interesting though. I mean, if it's generic, but I mean, why couldn't I mark an object in managed code to say I want to have control over when the garbage collector. I tell the garbage collector when this thing's ready to be killed, and the garbage collector will collect it. What you're saying is, well, the garbage collector just doesn't go collect individual things. You run sweeps.
Right, and that's not safe if you try to tell it, because if you passed it to another person, or part of code, then you can't know that, and therefore you would expose bugs that would crash the program.
Excellent. So let me ask you this. I mean, why did you get into garbage collection, and what's so exciting about this for you? And what's your history?
For me, I've always been working in runtimes. I mean, I worked on Lisp for a long time. I worked for Schlumberger, and they were big on expert systems. They were developing expert system in Lisp, and I helped them transition from Interlisp workstation to DEC workstations at the time, which were running DEC Common Lisp. Then I worked, and garbage collection was, part of the Lisp experience. Then I went to work for Texas Instruments in Austin on TI Explorer, which were one of the Lisp workstations that were common at the time. And there I worked on all of the runtime aspects, the system internals. So both the libraries, the interpreter, and the garbage collector. And then I worked for Dussud, where we had a IDE to develop C++ for Sun workstations. And there we had a complicated network of objects. Essentially, we had an in-memory database to represent program element relationships. So a function would call 5 other functions, you record this, and we were able to do incremental compilation based on just the modification of few functions. So if you modify a function, then what depends on its structure needs to be recompiled, and we knew that. Or you add a member to a struct, then everybody who used this member in a way that they knew the length and they were access to it, then had to be recompiled, and we knew that.
Excellent.
And so essentially it's a large network of objects that have cycles, and the fact that we didn't have a garbage collector in there was a big problem, and we suffered. We had many cases where we weren't clear. We had bugs of ownership, and we would delete an object and the object was needed. So that was really painful. So when at Microsoft I studied on the VB runtime, and the VB runtime isn't collected, but it's automatically managed. It's managed by an automatic insertion of address and release, and it works well. The only problem is address and release is not scalable, because the release part needs to be they need to be locked operation, because you need to make sure that the count is accurate, even if you have two concurrent threads adding. So the overhead by an automatic memory management of the style address release was really big. So I did measurements there and say, yeah, that's really hard. And if we were to go to multi-threading, then it would kill us, because we would have to have interlock increment, interlock decrement, instead of just the increment and decrement that we used to have. So when we started on VBScript and then on Java, then we knew that we had to do that.
Excellent.
And to me, I'm very attracted to it because it's a high leverage point. It's something that if you do a good job, your program will run a lot faster. In a way, it's more leverage than optimizations. Program optimization in C++, if you have a very good optimizer, you get 5% faster code. Say, oh, great, our program is 5% faster. GC can affect by 30%. So it's highly leveraged. And the challenge was when I started my work there is that servers didn't have good garbage collectors. None of them were scalable at the time. And the challenge was to make one that was transparently scalable and would adapt to different workloads. And to me, the work is undone. We have a lot of work. For example, one of the questions there was... I can't
Let's see
remember who
it.
asked it.
Let's do it.
Okay.
What was one of the questions and who asked it? Let's see here. All right, Niners. Oop, well. There we go.
All right, that was the question about latency. Right, so Stebet
Okay.
is making the point that GC is one of the factors that picks against managed code for multimedia. And that's certainly true. GC can entail pauses, and a pause is essentially a point where the program doesn't make any progress, doesn't execute any user instruction, is just busy doing the collection. And as I said before, in order to go through the stack, we need to stop the stacks. And in order to have a consistent view of the graph of objects, so we are sure we don't miss any, generally we stop the app. So we introduced a mode which is called a concurrent mode. And the concurrent mode tries to stop the program at a number of points, but during small interval. The problem is there are significant number of situations where get defeated. So instead of stopping the program for a small amount of time, we stop the program for a large amount of time. So that's an ongoing battle with GC. That so we are going to introduce a new way of a concurrent collector in some future. So that's very advanced work we are doing to address that. So essentially, we will get to a point where we can have pause time that are in the order of few milliseconds. And for most well-behaved programs. Right now it's a challenge to find a well-behaved program that will exhibit that. I can write one. You can just new object and not use them, and so they're all dead. And if you run that, you will see that the pause time of this app is way lower than a millisecond.
Okay.
The problem is when you start using these objects for a period of time, so they get harder and harder to collect because they get globbed amongst other objects that don't go away, and then you need to separate them out. And the ultimate way to separate them out is do a full collection, which is done in concurrent mode, but entails those long pauses when there is significant work needs to be done by the app. So there is a lot of research done in that, and we are doing our own direction that seems to be going pretty good. That's something to look forward in the next few releases.
But I mean, it's a hard problem. So basically what you're saying is, I mean, in order for an executing process, an application to have its detritus removed, right? Its objects collected,
exactly. Yep.
It has to pause so that you can actually access that memory and clean it
and
up.
so there are ways to simulate snapshots. And so essentially, if you posit a minimum of time just to create a logical snapshot, then you don't need to posit much longer. The problem is, if you don't collect anything on a short term, then the short term will accumulate. And that's what's happening right now with our concurrent collector, is that the Gen 0s don't get run while the Gen 2 is chugging along and the app is chugging along. So new garbage gets created but doesn't get eliminated. So the memory footprint grows, and at some point we say, stop, we can't go forever. So every allocating thread will have to stop until the concurrent collector is finished.
Okay.
So that's something we are addressing in the future, and say it's under development right now. We are not even sure that it's going to pan out. I mean, we have good hope, but it's a long way to go.
It's a long-term project.
Right. So we know that. Another headache for us, or another area of opportunity, is very large server space. So servers work very well, but there is a cost to the full collection on the servers, and the full collection is divided amongst all of the processors that are available on the machine. But it turns out so far that the trend so far has been to get more memory faster than more processors faster. It may disappear with multi-core, like when we have 32 cores per chip, then maybe that trend would invert. But right now, it's easier to add 32 or 128 gigabytes of memory on a 64-bit machine rather than add 32 cores. And so essentially you end up having more memory per core that we've ever seen. And that introduces a significant pause that translates on a server in a request latency. So essentially all requests come and go very fast, and then the server becomes temporarily unavailable. The requests don't complete until the garbage collection finishes, when a full collection happens.
Interesting.
So there are various ways to mitigate that. It turns out that if you have several servers and you have a load balancer that is based on request time, like some load balancers do that, then automatically the load balancer will move away the incoming request onto a server that is currently engaged in a Gen 2 collection and move them to other servers, and then as soon as the server starts responding, then the load balancer will direct request onto it. So it's an okay situation. It's not something that bankrupts servers, but it's something that is worthy of attention. And there have been research in this area, and that's something that we are very interested in working on.
Absolutely.
So the future, the nice thing about garbage collection is that it's a cutting-edge technology, and it helps people. Many people, are given very high compliment on how our garbage collector works, and that's very nice to hear.
Sure.
On our end, we know that we can do more, and certainly we are working more. So it's not something that you just do and forget. That's something you get engaged and then you work many years on it.
Absolutely.
By the way, I am not actively developing anymore.
You're not.
I'm the architect, but I am, the amount of code that I develop for it right now is very small, and we have a new developer, and she has a blog that is very interesting and very well. Maoni Stevens.
Excellent.
And she has a MSDN blog, Maoni, that is very well regarded as far as sources of information for the garbage collector.
Excellent. Well, we'll get her on here sometime.
Right.
Huh?
Yeah.
That'd be great.
Right.
Cool. But I mean, you created the first one.
Right.
You're still deeply involved.
And I am architecting the future of them.
Fantastic. So, do you ever see a future where garbage collection is going to be sort of, or a garbage collected runtime is going to be in par with, a human collected runtime, meaning developers that actually write the code right to the metal?
We are already on servers. Now, all of our properties at Microsoft, they are all running managed code. We had MSNBC was running on our premise, but written by some people external. They had terrible problems with essentially memory fragmentation on servers. So the server will run really fast for the first 5 minutes, and they had to reboot it every 15 minutes because fragmentation was killing them. And when they moved over to ASP.NET, ASP.NET itself was the path length, the number of instructions required to execute the same request was longer because managed code has some inefficiencies that we are working to eliminate, but had some in code generation, and the fact that it types safe, introducing some checkings. And they found out that they would run even faster for the 5 minutes, and then they ran forever, so they didn't have to reboot. So I believe on server it's clearly obtained. I mean, it's a little bit like, running assembly code versus compile code, and you can win in very small areas, and you say, oh yeah, that compiler is dumb here, that inner loop, I can write it better. But you are not going to write the entire program, and if you do, then you are going to fail because it's too much to write, and then you produce an error that completely just throw the entire program.
Absolutely.
So I believe we are there, and we have a lot of benchmarks that tell us we are there. What people tend to compare is micro-optimization on a specific part versus the whole program. And I mean, people have to remember that the garbage collector takes the whole app as a whole and trying to optimize it, rather than optimize few places to the detriment of other places.
Interesting. Now, for certain applications, in the cases like the media application that he was talking about,
Right.
Certain operations are going to be the ones that need to be
Right.
highly optimized.
And for example, for that we fully support modes where you can execute some of the code in unmanaged code, and therefore there is no latency, because when we stop our threads and we find out that they are in executing unmanaged code, we restart them right away. So if a thread is rendering in unmanaged code and it was resulting from a code from managed to unmanaged, then they won't see any latency there. And if we look at the architecture of WPF, for example, WPF has a clean separation between the rendering at the low level and the object model of all of their graphics objects. And the low-level rendering is done by unmanaged code and doesn't suffer any latency, so animation in there works great. And then the high-level objects are done in managed code, and they feed essentially instruction onto the unmanaged part, which does the low-level rendering. And that's a very nice separation.
Absolutely. that's
and that works very well.
Excellent. So let's see you got any other questions in here? Let's see what we have here. Real time hunting for questions with Patrick Dussud. All right. Let's see. A little guru had a bunch of things. I know he up in. Let's see.
Okay. One of them is interesting.
Yeah.
I think there is a misconception. People believe that when you call GC collect, it's up to the collector to either ignore it or run. It turns out that every call to GC collect is imperative. We actually run the collection. And what's happening is that if it's a concurrent collection, then the call returns right away, but the connection is started. So maybe that's where the misconception comes.
Okay.
So sometimes it happens, the collection happens too fast, and then your program stalls later on. That's because actually we are in concurrent mode, and when you say collect to or collect with no arguments, then we start the collection and we return. And if you collect generation 0 or 1, those are not concurrent, and the call will return after the collection has been performed. Usually the collection takes less than a millisecond or less than 10 milliseconds for Gen 1, and so the call is very quick. But in general, people shouldn't be calling garbage collect explicitly, and the reason is that the tuning engine observes the rate and observes the efficiency of the collection. And when additional calls are made, then it throws off the computation of the efficiency. And if a collection just happened naturally and the programmer calls collect right away, then we get very few objects in between that are likely to be live because it just got created. And therefore we say, oh, that wasn't worth it, and maybe we should back off. And it throws that kind of natural rhythm that we try to develop.
Interesting.
The other part is it's expensive. So if it's done too often, and it's hard for people unless they are controlling the whole app, it's hard to know that if they do it in one routine, it's hard to know that this routine won't be called 1,000,000 times a second. How can you know if you are not the one who controls the whole app?
Sure.
So it's certainly very hard to do at the level of a class library.
So let me ask you, I mean, there's really, it begs two questions. The first one would be, why did you expose a public collect? And secondly, when I call collect, am I collecting, is the GC is only collecting relative to my execution context? Yes?
Right. So it will, it's at the level of the whole address space. So even if you have several app domains, all app domains are collected at the same time.
Very interesting.
So it's per process, essentially. It's process-wide.
Okay.
And why do we expose it?
Yeah.
Well, that's interesting. I mean, it's actually used in some resource management problems. So suppose that you have precious resources, such as database connections, and you need an infrastructure to convince the collector to collect at all costs if these needs to disappear automatically. So we have an infrastructure to do that, and it's written using explicit call to gc.collect.
Okay.
I mean, generally people believe that they have to do it when they perceive that the GC doesn't keep up with the app. And I've heard that term, and I've seen in blog this term, and it's actually not possible in general. What's happening is that GC is triggered by allocation. So you can allocate, and then at some point an allocation will trigger a GC. So GC has to keep up with the app because GC feeds off allocations. So it's not possible for GC not to start if you allocate. If you allocate, GC will start eventually. And what seems to be happening is two things. First, the program itself could have leaks. And so memory just accumulates because some references exit from a static variable to a large thing that is growing because it's a list or something that is growing. Generally, when you call collect, then you don't get more. So, but another very insidious source is com STAs. So the problem with com is that we call into com, and com uses unmanaged memory, and we do that transparently. To the user, it doesn't seem like you are calling into a com object. It looks like a normal CLR object because we have a little proxy that is transparent that stands for the com object. And some com objects can only be deleted from the thread which created it. So if you have a main thread that is really busy creating objects, then this thread will not give any time, will not wait or pump messages long enough for the finalizer thread to get back and say, hey, you need to kill these objects because you created them. So these objects don't go away and accumulate, and then the memory grows and grows, and it looks like GC is not keeping up. In reality, what's happening is GC is piling up work to be done by the finalizer thread, and the finalizer thread needs to make a remoting call to the main thread that is too busy to accept remoting calls. And usually making a call to wait for pending finalizers, pump messages, and if you insert this instead of a gc.collect, then the problem goes away. The problem is even wait for pending finalizer is quite expensive if there is work to be done. And the best way is to eliminate the use of single threaded apartment com components and use instead a multiple threaded apartment, MTA, multiple threaded something.
Sure.
It's not apartment, it's something. Yeah, multiple threaded objects.
Sure. Excellent.
So that's but if there is any case where calling GC explicitly helps to avoid a growing the memory, then we'd like to know about it because that's a bug. That's something that I need to understand and we need to fix.
Well, and that actually brings up a great point in the sense that when you're writing a generic object maintenance platform,
right,
which is a garbage collector, and it happens to be based on, an infinite number of potential objects, right?
Right.
I mean, objects can be of any type, right?
Right.
That's the whole
Right.
idea. And the interaction between them can be very complicated. Right. So you have to be able to understand when the right time to remove them is.
Right. So
it's
essentially
exceptionally challenging.
Right, and that's what we spend years on doing, and that's where the purpose of the policy engine is. Essentially, try to identify the situation where we need to start a collection in order to minimize memory, maximize program efficiency.
Certainly, and I would assume that over the years, I mean, your garbage collector has been running now since what, 2000, 2001?
Right, something like that, yeah.
And there's probably been some pretty interesting scenarios that you didn't think of ahead of time.
Right, and usually the way it goes is we find an app that either is using too much memory or is spending too much time in garbage collection, and we try to get the app and instrument it, find out if it's because the behavior of the app is hopeless, because the app is written in such a way that you need to create 100 megabyte trees and then delete them, and you need to repeat that all the time. Therefore, you're going to spend a lot of time in memory management because that's the profile of your app. Or it's because, we could do better, but we are fooled by this situation or that situation.
Okay.
And for example, one of the area that we worked a lot is to try to work well in when we are close to being out of memory from as far as the OS is concerned. So when the memory load is very high, and we try to essentially collect more, be more frugal about the memory we have when we are in those high memory load situation. And these have been ongoing, and I can't say we are perfect right now, but we are a lot better than we used to, and we are getting better all the time.
Excellent. So now, as you mentioned earlier, so the more memory that a system has, the harder your job is.
Right. Yes. And one of the paradox is that essentially the efficiency of the OS and all of the apps will go down dramatically when the apps tries to keep going under paging, because paging affects everybody, and LRU is not necessarily a very good predictor of what pages should be swapped out. And so avoiding pages, if we can avoid paging versus going to paging, then it's worthwhile spending more CPU time to avoid paging rather than paying all of the disk latency and CPU at the OS level, at the VM manager level. So we have spent a lot of time there, and we are actually requested the OS to provide a notification for low memory. And we asked that, we finally got it. I think, can't remember, maybe for Windows 2000. It was introduced there, and we use it. So we wait for that notification, and then when the notification comes, then we try and switch into a very frugal mode.
Excellent. All right, well, let's take a look at maybe one more question here, and then I'm sure you have to get back to architecting the future here.
Oh, one of them is what's the best practice for performance-sensitive app like 3D XNA games?
That's
So-
Min H. All right.
Okay.
So
Right.
what's that?
So essentially, objects that it's very cheap to create an object. We can create object at essentially memory bandwidth speed. What costs is the number of bytes that we end up having to clean up to get a nice little object that is type safe, where it's clean, it doesn't have bogus data inside of it. And so creating an object is very fast, but what counts is the number of bytes that your object has. So one thing is to allocate the absolute minimum that you need. In the old days where rounding up allocation would diminish fragmentation, and people used to do that. Oh, I'm going to allocate only 4 bytes and then 16 bytes and then 64 bytes, because if they are all of that size, then they can neatly fit inside of each other, and you reduce fragmentation. With GC, it is not the case. You pay per byte you allocate.
Interesting.
And so allocating the least amount. The second is make sure that an object which dies very quickly is very cheap to reclaim and very efficient to reclaim. And if you push it to the limit, it would make sense that if the object would be created in an area where the cache is already there and died there, and the memory completely reclaimed, then you would stay in the cache. As I said earlier, it's not as rosy as this, but you can tend towards this. So essentially, if you allocate object and you make sure you don't hold on to them longer than you absolutely need to, then you get good performance. However, you can still have long-term data. So if you have data that stays forever for the lifetime of the game, or almost the lifetime of the game, maybe when you go from a game phase 1 to game phase 2, then the data changes, but otherwise is stable. It's also very good, because essentially this data will be in the Gen 2 area, and there will not be any pressure to collect it, because no new things comes in it. So if you allocate something and it's fairly static, and on the other hand you allocate object all the time that die very quickly, then you get an excellent situation. You will get very, very few full collection. A lot of Gen 0 collection that are extremely efficient will cost you nothing. Excellent. So that's the best case. And the worst case is what we call middle-age objects, are the objects that you hold on to but eventually will die. For example, one of the worst case would be some kind of cache where you just replace. So the cache you replace every 10 minutes, you replace some old items. Mm-hmm. So these old items are guaranteed to be in the Gen 2 heap because they are old enough to be promoted there. But then you make them die and you create new ones to replace them. And that's not a very good mechanism because you end up putting pressure on the Gen 2 area where you just introduce new object inside there. And there is significant garbage to be collected. So the garbage collector will do his job and do it. The only problem is it costs.
Interesting. Now, is there a range? I mean, for example, I could see in a server environment,
right,
for like on a website, I know, for example,
right,
like Channel 9,
right,
there might be a cache that you don't want to expire very often at all.
Right, exactly.
Now, so but when it does get expired,
and it's
not
done
a big
to
deal.
be exactly. If you do it in big chunks, that's fine. That's the slow death that kills you.
Okay, excellent. So one last question I wanted to, and this was sort of brought up. This was definitely brought up on the Channel 9 thread. Was with the advent of Silverlight 1.1,
right.
We now have a sort of a stripped down CLR.
Yes.
What's
and
that
so
garbage
what's
collector?
great about it is that Silverlight is essentially heavily borrowed from the CLR. It's a stripped down with the literal sense of the term. Mm-hmm. We have the same source base. We just don't include all the files. So the garbage collector that is in there is only the workstation one, not the server one. But it has the concurrent collector and the non-concurrent on the Windows side, and the non-concurrent only in the Mac side because we don't have some OS services that we need to implement the concurrent collector efficiently.
Interesting. And so on the other platforms, do you get the OS message of memory, out of memory impending doom? Out of memory, it's an interesting point because you have to communicate with, say, I don't know what the Mac kind of event it would give. Like, for example, Windows tells you, hey, I'm running out of memory.
Right, that's one of the areas that we don't have, right? Okay. And in general, however, for Silverlight, it doesn't make much difference because when the heap is smaller than 16 megs, concurrent collection doesn't help.
Cool.
So for Silverlight, majority of Silverlight apps, it's a good collector.
Absolutely. Excellent. Well, it's a great collector, man, and thank you very much for creating it.
You're welcome.
And I look forward to seeing how it evolves. I mean, maybe someday, managed code will just be the thing to do. And as you mentioned earlier, you used the term right during the very beginning, which was composable.
Right.
And that's the future.
Right. Exactly.
And you need to have a base that has that, like the work that you're doing. So I can build my buildings.
Exactly.
And not have to worry about what's going on in the plumbing.
And one of anecdote on that is that we believe that the .NET framework is extremely successful and people reuse it a lot. And we got the Exchange, the new Exchange server, Exchange 12, is mostly written in managed code. All of the new code that they wrote was written managed.
Nice.
And the storage engine that they use hasn't been rewritten, so it stayed in unmanaged code, but the rest in managed. And what they told us that they were ready to re-implement all of the collection classes because they said when our unmanaged code worked, none of the unmanaged code classes actually worked for us because they were not that composable. So we try STL, we try MFC, none of these things. They had little problems with them that made it non-usable, so we just wrote our own. And we were ready to write our own, but these worked, so we just kept them. So essentially they didn't re-implement the low level, they just used those modules and they worked.
Outstanding.
So it's a great validation for our approach.
Absolutely, I should go talk to those guys.
Right, yes.
Perfect. Well, hey, thank you very much for your time. Really appreciate it. Great job, man.
Great, thank you.